In this video, we're going to go over how to analyze effectively every type of loop that you are likely to see. We're going to go through each of these trying to explain all of our steps along the way. We're going to begin with a relatively daunting problem. I'm going to assume that you've seen some loop analysis before, and in this video I'm going to focus on sort of all of the things that might show up along the way. So here we have a triple for loop that shows up, and the bounds of the for loop are a little messy looking. To analyze any problem involving loops, our goal is to always try to write the loop as a summation. We have lots of tools for analyzing summations. There's the entire field of combinatorics to draw on, and you likely have seen several different ways of analyzing these. So let's begin by converting these for loops into summations. This is done exactly one-to-one matching up, where each for loop gets translated into a summation with the exact same bounds as the for loop. So that first for loop gets translated verbatim, the next for loop gets translated verbatim, and the final for loop gets translated verbatim. What goes inside of the summations? Well, what goes inside of the summations is the cost of the code that is executed every time the for loops execute. In this case, that's line 6, this line here. And the cost of executing that line of code is going to be some constant. It retrieves values I, j, and k, and x, and assigns, and does basic adding and subtracting. All of those are assumed to be constant time operations. When analyzing nested summations, you always want to begin with the innermost summation. So in this case, that means starting with this summation here. We begin by doing nothing to the first two summations. In fact, to demonstrate that, I'm literally going to copy and paste them. And then that innermost summation, to analyze summations, the easiest type of summation is one where the inside of the sum does not depend upon the loop variable. So in this case, k is the variable for the summation. If you look, k does not appear inside of that summation. Therefore, we're adding up some fixed quantity c a fixed number of times. So we take the sum and, the thing inside of the summation, and multiply by the number of terms in the summation. The number of terms in a summation is the top bound of the sum minus the bottom bound of the sum plus 1. So in this case, that would be the top bound, which was ij squared, minus the bottom bound, which was I, plus 1. And now we would proceed doing the exact same thing with the next sum. We ask, does j appear inside of the summation? In this case, it does. So we have a variety of tools we might use. You can analyze this by using formulas. There may be known formulas for the expressions that appear inside. For example, you might know the sum of an arithmetic sum, the sum of squares, the sum of cubes, or a geometric sum, or you might even try to bound the summation. In general, I will recommend bounding because it works universally, where trying to use formulas works in some cases and not in others. So we're going to begin trying to bound this summation. Notice our goal is only to determine the complexity. To determine the complexity, we don't care about the exact value of the summation, just what are the summations in theta of. So I'm going to start by bounding above. Bound above. Our primary technique for bounding above is to replace every term in the summation with the maximum value in the sum. However, the maximum value in the sum, in this case, if we look at the j summation, is this 4i plus 3 term, which is a bit messy. So instead of dealing with that term as written, what we can do is we can actually make the sum bigger when bounding above by adding up more terms. So what we're going to do is do nothing at all to the outermost summation. We're going to leave that unchanged. We'll deal with that later. And then the inner summation, I can increase the range of values. There are two ways in which you can do that. You can either decrease the bottom bound, so I can make this bottom bound go down, or I can make the top bound go up. As long as I increase the range of values, I will make it bigger. So what I'm going to do is take that bottom value and make it something more convenient. I might be tedious to deal with, so I'm going to replace it with 1. 1 is in general the best bound you can have in the bottom of a sum. Most formulas work very well with 1, and things will cancel out nicely in general if you make the bottom bound 1. I'm going to change the top bound to be something that looks similar, asymptotically speaking, but is more convenient. So something that looks similar, but is more convenient asymptotically might be 4i plus 3i. Where on earth did I come up with that? Well, 3 is definitely smaller than 3i, eventually, for larger values of I. I starts at n, so I is presumably quite large. So this is definitely going to be a larger value. And then the inside of the sum we're going to leave entirely untouched for now. So we have c times ij squared minus I plus 1. So to denote what we did there, we might move this over a little bit. What we have done, which we will annotate for you, is we've increased the range of the sum. Increase range. What I mean by that is we've added up more values. So that's the first thing we're going to do. Another thing you can do to make sums convenient when bounding above is to get rid of negative values. Negative values tend to be a bit of a pain because they're going to just make your sum and the sum look bigger. And in general, they shouldn't be the dominant term because we aren't expecting the negative things to be dominant. Sometimes they might be relevant in that things will cancel each other out. But in this sum, that will not be the case. And usually it won't. If at some point you realize your bounds aren't going to match, you can go back to the drawing board and undo getting rid of the negative terms. So the next step I'm going to do is going to be take that exact expression I had, and I'm going to keep everything exactly the same, except I'm going to eliminate the negative term that appears inside of the summation, so that minus I is getting deleted, and then everything else remains the same. So what you can do is you can drop negative terms. The order of operations here isn't particularly important. Both of these are helpful, and the order in which you do them is not particularly relevant. The most important thing is that you do both of these before you do the next step, which is our technique for bounding summations. What we're going to do is replace every term in the sum with the maximum value in the sum. So we're going to keep everything the same. So we're going to copy down the exact expression we had, except every time we see j appear in the summation, we're going to replace it with the largest value that j obtains. By combining terms in that top bound, we get 7i, and then inside of that sum, to make it as big as possible, I will replace j with 7i. So we have c times quantity I times j is getting replaced with 7i, quantity squared now, plus 1. There are things we could do to deal with that plus 1. We might do that later, but for now we're going to leave it untouched. So if we look at what we've done, we've replaced every term in the sum with the max. So let's write that down so we can keep track of it. So we replace each term with the maximum value. And now, just as we saw with our first summation, the summation index, j, no longer appears inside of the summation. We've eliminated it from the problem. So the summand has become a fixed quantity, something that has nothing to do with j, so we can take whatever appears inside of the sum and multiply by the number of terms in the summation, just as we had done before. So t of n is less than or equal to that outer sum we keep untouched. And then the inner sum is the top bound minus the bottom bound plus 1. I could write out what that is, but by design, the reason I changed the bottom bound to be 1 was that when I do that top minus the bottom plus 1, the 1s will cancel for me, and that is very convenient. And then the inside of the sum becomes c times I times 7i quantity squared is 49i squared plus 1. And you can see the constants here might start to get a little ridiculous. Thankfully, the numbers don't particularly matter, so you don't actually need to multiply everything out. All that we really care about is that they are positive values. So beyond that, the exact numerical values are not particularly relevant to us. So this is the exact same step we had done before, and now we just rinse and repeat. We're going to do the exact same steps, but with I instead of j, and see where it leads us. So the next thing I want to do is to expand that range of values. I'm going to do both of them. I'm going to change the bottom bound to be 1, and the top bound is n squared minus 1. I can make that bigger by making it n squared, and that's much, much more convenient. So we change it to n squared. And then the inside of the sum I'm leaving untouched. So we have 7ci times, we have 49i cubed plus 1. And what we've done there is the exact same first step we did before. We expanded the range. Expand range. I believe I might have called it increase range before. The exact wording isn't important. The idea is that we increase that range, we expand that range of values, therefore adding up more things, therefore making the entire summation bigger. The next step that we did before was to drop negative values. I'm going to show you something else. We could have done this earlier, but it's nice to sort of separate these things and not do them all at once before we get moving in a problem. One other thing that we can do is you can, just as we did with the upper bound of the previous sum, you can change the +1 in this problem, the +1 that appears here, into something that is more convenient and can combine more like terms together. So what I'm going to do is change that +1 to a +i cubed, which again is definitely going to be bigger. So t of n is less than or equal to the sum from I equals 1 to n squared of 7ci times quantity 49ci cubed plus I cubed. What we've done there is make the sum and bigger. So we make sum and bigger. Sum and meaning the thing inside of the sum. We make that bigger. We have 49i cubed plus I cubed. We can combine that to 50i cubed. I'm doing that in place so that I don't need to rewrite a lot. So I'm going to combine them and write that as 50i cubed. And now I'm just going to factor out all the constants. You can always factor constants out of summations. So t of n is less than or equal to 7c times 50. And then the inside of the sum becomes I equals 1 to n squared. We have an I times I cubed left inside. That's it. So we have I to the 4th. And now all that remains to be done is to do the exact same steps that we did before. The step we were using there is what we call linearity. Linear operators are ones where you can distribute them across addition and subtraction and can factor constants out. The summation is a linear operator, so we can do that here. Just like an integral, just like a derivative, just like a limit, all those things you've hopefully seen in calculus, the same thing applies here. Now we're going to replace the sum with the biggest term. The biggest term here occurs when I equals n squared, the largest value. So I replace every term with the max, just as we had done before. So t of n is less than or equal to 7c times 50. And then we have the sum from I equals 1 to n squared. We replace I with its largest value, which is n squared. And just as we did before, what we're doing is replace each term with the max. So let's replace each term with the max. And now if we look at what we have, we no longer have I inside of the summation. The sum and only pertains to n. Therefore, we can take the sum and multiply by the number of terms, just as we did before. And we get t of n is less than or equal to 7c times 50, whatever that value is. I don't care. That sum is the number of terms is the top bound minus the bottom bound plus 1, which is n squared. And then the inside of the sum is n to the 8th. So hopefully at this point, we can see that we have n squared times n to the 8th. And there's no more summations, so there's no sort of concern going on that we might have oversimplified. We've got a closed form expression. With this closed form expression, we can now just identify what is the complexity. At this point, I feel comfortable saying, yeah, that definitely looks like we're going to be in big O of n to the 10, because we were bounding above. And now we need to bound below. Notice this is not a fast process. There's lots of steps along the way, but we're just repeating the same process over and over again. I can make this as symbolically messy as I want, but the process will remain the same. The numbers might get bigger, the expression might look uglier, but the process here is the same regardless of the problem. Now let's begin our bound below. So when bounding below, we need to go back to wherever we started bounding before. So if we scroll up, zoom out and scroll up, we notice All the stuff in red, thankfully I color-coded this for myself, is all the things pertaining to bounding above, which means when I start bounding below, I have to start back from this last thing I had written in black. So, just as we did when we bounded above, we're going to effectively do the exact same steps, but making things smaller instead of bigger. There are a couple of instances in which we need to be very careful because we need to make sure that our bound will match our upper bound. So, let's take this expression and copy it for ourselves so we can have it readily at hand. So we copy that summation. We'll paste it here so that we can see it easily. And now we need to figure out what to do. In our previous problem, the first thing that we had done was to increase the range. When bounding below, we can do the exact opposite thing and it works out exactly the same. Instead of increasing the range, we can decrease the range. So the first thing I'm going to do is take that summation, the innermost summation, and adjust it. The outermost summation, the one going from n to n squared minus 1, remains untouched. The inner summation, for a reason that will become apparent in a second, I'm going to leave that bottom bound as I, and the top bound I'm going to reduce down to 4 times I. And then the inside of the sum I will keep untouched, so that's c times ij squared minus I plus 1. And just as I said out loud, all we're doing is decreasing the range. So when we're decreasing the range, that means either make the top bound smaller or the bottom bound bigger. We're decreasing that total range of values. Now, just as we did when bounding above, we can actually drop positive terms with a little asterisk. We can drop the non-dominant positive terms. Hopefully looking at this, we can see that we have an ij squared and a 1. Ij squared is definitely going to be bigger than 1. So the term I can drop is the 1, but that ij squared has to stay in the problem. I need to keep all these most important things in the problem. So the next thing I want to do is to drop the positive terms. So again, leaving that outer summation entirely untouched, we go from n to n squared minus 1. The inner sums bounds are now going to remain untouched from I to 4i. Then we have c times ij squared minus I, and then plus 1 we're getting rid of. We can drop positive terms. Drop positive terms. With, again, the little asterisk, which I will include but not write down, that you don't want to drop the dominant positive term. Now, what we want to do is replace each term with the min. The thing that we needed to be careful of here, and the reason I didn't adjust the bottom bound in any way, is that when we bounded above, if we scroll up and see what we did, the value that we plugged in, let's highlight it even, we plugged in 7i. That's the value that we plugged in. It looked like, asymptotically speaking, I. When we bound below, the value we're going to have to plug in to make it small is I. Asymptotically speaking, 7i and I look the same. They have the exact same complexity. Had that not been I, we would have had to decrease the range in such a way to make that bottom bound look like the top bound, asymptotically. So, had the bottom bound been square root of I, had it been 1, had it been 15, had it been something that did not look like I, you would be required to increase it to something that looked like I. That could be I over 2, that could be I over 3, that could be I over 5, that could be I over any value. It doesn't really matter the constant, just I over something or I times something that will make it look like I. That's all we need to do. So here, the bottom bound conveniently already looked like I, so we did not have to adjust it. If it didn't, you will have to increase that bottom bound up to something that looks like I. The typical thing to do is to increase the bottom bound to whatever the top bound was divided by 2. So in this problem, had we needed to do that, we would have increased the bottom bound to 4i over 2. That is the standard technique. However, we did not have to do that here, so we're thanking our lucky stars we didn't have to. We will have to do that later, but I want to mention it now. All right. Let us bound below by replacing everything with the min after that long-winded explanation. So we have the sum from I equals n to n squared minus 1, the sum from j equals I to 4i, and I'm going to replace j with the value that makes the inside as small as possible. In this case, that value is I, as we've said 4,000 times already. This is c times I squared when we replace j minus I. And now that's the exact same step we did before. Instead of replace each term with the max, we replace each term with the min. So replace each term with min. Replace each term with min. And now, just as we did before, j is no longer inside of the summation. The sum and now only pertains to I. Therefore, we just take the sum and, the thing inside of the summation, and multiply by the number of terms. So we get T of n is greater than or equal to the sum from I equals n to n squared minus 1 of the number of terms, which is the top bound, minus the bottom bound, plus 1, times the sum and, which is c, times I cubed minus I. And now, just as we did in our previous problem, we are going to redo the exact same steps before the next summation. This is just doing the same thing over and over again for each summation you have to deal with. So the next thing we want to do is to drop the positive terms from the inside of the summation and maybe combine some like terms. If we look, we have 4i minus I, that's 3i. And then we have a plus 1, we can drop that positive term, times c, and then we have I cubed minus I. So that's dropping the positive terms. Drop positive terms. With, again, a mental asterisk that we have to keep the largest term to make sure we don't accidentally make it too small. And now we need to decrease the range of values. So let's do that. And this is an instance where I have to adjust the bottom bound. The top bound, I can't come up with a convenient way to decrease that. There are ways I could do that, but I'm going to leave it as n squared minus 1. So the top bound is going to stay n squared minus 1. And I want to increase the bottom bound, make it bigger, and make it look like n squared somehow. The standard technique is just make it n squared over 2. You could make it n squared over 3, you could make it n squared over 4, you could make it n squared over 33. The number does not matter. You're just making it look like n squared somehow. And then inside we have 3ci times quantity I cubed minus I. And the thing that we did there was decrease the range or shrink the range, whichever active verb you want, decrease the range. And now, just as we did with our upper bound, we're going to replace each term with the min. Well, do the same thing again, I guess. In our upper bound, we replaced it with the max. Here we want to replace it with the min. So we're going to plug n squared over 2 in for I. So we get T of n is greater than or equal to the sum from I equals n squared over 2 to n squared minus 1 of 3c, replace every instance of I with n squared over 2, and we get 3c times n squared over 2 times quantity, n squared over 2 cubed minus n squared over 2. And just as we did before, all we're doing there is replace each term with the min. Replace each term with the min. And now, just as we've seen many times already, we no longer have I inside of the summations. This is now a fixed quantity that we're adding up. It's the giant mess, but it's still a fixed quantity. So we take that fixed quantity and multiply by the number of terms, which is the top bound of the sum, minus the bottom bound of the sum, plus 1, times the inside of the sum, which is 3cn squared over 2, times quantity, n to the 6th over 8 minus n squared over 2. And at this point, in the previous example, we had a bunch of really nice looking things. However, in our lower bound, we've got a bunch of constants. There's some nice cancellation maybe. You can identify that the minus 1 and plus 1 cancel. You can also maybe identify that n squared and n squared over 2 are going to combine in a convenient way. So if we look at this, let's identify the complexity. We don't need to simplify. All we're trying to do is determine the complexity. We're not trying to formally prove it. We just want to find out what the complexity is and justify it. Justify it well enough. So if we look at this, we see n squared minus n squared over 2. That looks like n squared. Looks like n squared times looks like n to the 6th. All of that taken together looks like n squared times n to the 6th. That is n to the 10th. That's very, very convenient because our upper bound was also in n to the 10th. So we get omega of n to the 10th. If you are in big O of a function and big omega of that exact same function, you are in theta of that function. So after all of this work, we can finally conclude that we are in theta of n to the 10. And after all that, I think we deserve to get a nice highlighting around that answer. So we have that as our final conclusion. If you could manage this problem, there is hardly anything you could see that would give you trouble. This problem encapsulates nearly all of the difficulties that can conceivably show up while analyzing for loops. Another wrinkle we can throw in is while loops, which we'll see shortly how to analyze those. We're going to rely on nearly all of the same techniques that we used here, though. This problem demonstrates all of the techniques you really need to analyze summations. There's a small asterisk there because there's some summations for which this technique doesn't work. We will see those shortly. Having seen sort of the worst for loops have to offer, we're now going to begin our foray into while loops, which are sort of a different beast entirely. This while loop here is stuck inside of a for loop, so we're going to need to use some of our techniques from for loops pretty much unavoidably, but we need to figure out how to analyze the while loop. I recommend when analyzing a while loop to manually track what the heck is going on as it adjusts the variable. The reason while loops are fundamentally different from for loops is that their variables don't just increment or decrement by 1. They change in some other way. In this case, the while loop is dividing by 4. You could be adding by a different value, subtracting by a different value, multiplying by a value. You could be doing whatever operation you want. Sometimes you might be taking the square root of the value. There's a whole bunch of options here. The best way to analyze it is to begin by just tracking the variable. So I'm going to keep track of how many iterations have executed for the while loop, how many times has it run, and I'm going to track what happens to the variable that is judging whether or not the while loop terminates or not, in this case, j. So, what is j initialized to? Well, the code just tells me. The code says j starts at I squared. So, initially, j is I squared. After the while loop finishes its first iteration, once the while loop has fully executed its first time, what happens to j? Well, j is updated by dividing by 4. So we take whatever value j had, in this case I squared, and divide it by 4. What happens after the second iteration of the while loop finishes? Well, after the second iteration of the while loop finishes, we will have divided by 4 again. So we take I squared divided by 4 and divide that by 4. So we get I squared divided by another copy of a 4, so 4 squared. And then, after some number of iterations, some variable number, it looks like there's a pattern emerging here. We're dividing by 4 over and over again. Continued division, or continued multiplication, is exponentiation. So, after k iterations, this is going to look a heck of a lot like I squared divided by 4 to the k. And it's going to look exactly like that, because we're continually dividing by 4, which will always lead to an exponential looking term. Well, why on earth is that helpful to me? That tells me after some variable number of iterations, what does j look like? What I care about is how many iterations. Well, I know the last value j could possibly take is 3i. So I could potentially use that to determine how many iterations. In particular, I know that this stops when I'm going to make a mathematical error here, but it's okay, trust me. It's I squared over 4 to the k. That's the value for j. It's going to stop when j equals 3i, according to the code. And then you're going to probably protest and say, well, no, it doesn't stop when that happens. It actually runs once more. However, we're just trying to get an asymptotic understanding of what occurs. My off by 1 here, or ignoring potentially floor functions or ceiling functions, is not going to affect the complexity unless I have some really, really ugly functions in this problem. And I don't have any ugly functions, no factorials, no comically big exponential things. Nothing like that is going to show up. So we're totally okay ignoring the fact that we might be off by 1 by simply setting this equal to 3i and not dealing with some more specifics that will occur. So it stops when this happens. This is a special value of k. K sort of represents this iteration. So one thing that can help avoid confusion is to give this special value of k some special signifier. You can either call it a different letter entirely, or you can just add a little decorator to it. Call it k1, call it k2, call it k bar, call it k prime. I'm going to choose k prime, but the specific decorator that we use is not relevant. I want to solve that for k prime. So I'm going to multiply by 4 to the k prime, and we get I squared equals 3i times 4 to the k prime. Divide by 3i, and we get I over 3 equals 4 to the k prime. I then need to solve for k prime, which is stuck inside of an exponent. To get things out of the exponent, we take a log of both sides. So take a log base 4 of both sides, and I get k prime equals log base 4 of I divided by 3. That k prime tells me the number of times the while loop executes. Conveniently, if we look at the body of the while loop, the code that executes every time the while loop does, that code takes a constant amount of time. So I can tell you the running time of the while loop. I know how many times it runs, and I know the cost, which is constant, of running a single iteration. So the cost of the while loop, and I'm going to lump in that j equals I squared, that's a constant amount of time, it's not going to affect anything, is going to be a constant. That's how much the body costs, these lines of code take constant time, times the number of iterations. So times that k prime value, which was how many times the while loop ran. So that c times log base 4 of I divided by 3 is the running time of the code I bracketed in, lines 4 through 8, the body of the for loop. Now that we have that, that tells me the cost of running the body of the for loop. For loops, as we mentioned in the previous problem, are very, very convenient. Their runtime can be determined by simply using summations. So I can express the running time of the for loop as a summation, going from the bottom bound of the loop, which was 5, to the top bound of the loop, which was 6n, of the cost of the loop, which is c log base 4 I divided by 3. And now we must repeat the exact same steps we had done in the previous problem. We're going to go through these quickly and then label them afterwards, just so we can do them all in one go, to show the case that, while it may have taken us a little while in the previous problem, these steps can be done relatively quickly if you're just marching through them on your own and not explaining them in a YouTube video. So let's do all of these steps. Step 1 is I'm going to expand the range of values. So I'm going to change the bounds to be 1 to 6n, and then leave the inside the same, 6 log base 4 of I divided by 3. After doing that, I'm going to replace each term with the max, so I keep the bounds of the sum the same this time, but replace I with the value that maximizes the inside. The value that does that is 6n. Having done that, I now no longer have I inside of the summation, and can take the number of terms, the top minus bottom plus 1, and multiply by the summand. So the number of terms, which on purpose is just going to be 6n, because 6n minus 1 plus 1 is going to give me 6n, times c log base 4 of 2n on the inside. And at this point, all we would need to do is identify the complexity. That looks like it is in big O of n log n. So our final conclusion for the bounding here is that this is in big O of n log n. And now let's really quickly just explain what the other steps were. The first one was expand the range or increase range. Expand range. And then we also replaced each term with max. Replace each term with the max. So the exact same process we used before. Now we also need to bound this below. So let's go through and do that. Let's draw some sort of dividing line for ourselves here so we can easily separate it. Now we must bound below. The first step I'm going to do is going to be to adjust the bounds of the sum. The sum starts at 5. I want to make it start at something that looks like n. So just as we did in the previous problem, let's just make it the top bound divided by 2. So in this case, we're going to make it I equals 6n divided by 2, which is 3n to 6n. We shrink the range of values for the lower bound. The inside remains the same, c log base 4 of I divided by 3. And then after we do that, we are going to replace each term with the min. So in this case, the value that minimizes the inside is going to be plugging in the bottom bound. So this is c times log base 4 of 3n divided by 3. And now all that remains to be done is to take the sum and multiply by the number of terms, just as we did before. This is greater than or equal to the top bound minus the bottom bound plus 1 times the inside, which is c log base 4 of 3n over 3 is just n. And hopefully we can look at that and go, that's going to be 3n plus 1 times log of n. That's definitely going to be an omega of n log n. Omega of n log n. Just as we commented on before, we are going to quickly write down what our steps were along the way now that we've done them. The first step was to decrease the range. Decrease range. And the next one was to replace each term with the min. Replace each term with the min. And if it's in big O of n log n and big omega of n log n, it must therefore be in theta of n log n. So, thus, t of n is in theta of n log n. And thankfully, this was much more reasonable than the previous problem. Part of the reason is I could have cooked up a bunch of terrible for loops to combine with the while loop, but that would lose focus. The while loop was the main focus of this problem. The while loop is not that bad when it is this inner loop. While loops tend to be much worse when they are the outer loop. We'll see that in our next example. But when they're the inside loop, usually it's relatively straightforward.